you can keep it as a homework. So now if the left hand side must be 0, so that must be satisfied with the right hand side of the equation. So if you take the divergence of the right hand side term minus del b over del t, so we have to calculate this divergence. So it must be equal to minus del over del t. So these are commutative in nature, the differential. So either you take the gradient or the divergence first and then differentiate with time, or either you take differentiate it with time and then take the divergence. So in any cases you should get the same result, because these differentials are commutative in nature. So we can write it as del dot b. We have taken out this term and kept the delta term inside. So because of commutation relation. So you know that del dot b is 0 from our second law. So the divergence, the derivative of 0 should be 0. So now you get that this is 0. So for the left hand side we know that it should be 0, and for the right hand side you are getting 0, because you are using the second law for justifying the divergence of the second term. So it's all okay. Now for the fourth equation, when we do the same kind of thing, then what we get? So the divergence of this term del dot del cross b, you will get this must be 0 by default. So by the rules of vector calculus it must be 0, but it must be equally satisfied with the right hand side. So the divergence of mu naught j, this term must be 0. So I am just taking the constant term outside, and del dot j. So we have to calculate this del dot j term separately. So let's calculate this del dot j. So to calculate this del dot j term, we need to write the definition of j. So you know that this j term is, we can separately calculate it. Let's calculate. You know that current equals integration of j dot, we have to calculate this term, not this, we have to find this. So current is defined as del dot j dot dA over a surface. Now current is also equal to dq over dt. Now you can write this q as d over dt of integration of rho dv. The charge density calculated over the volume, integrated over the volume, gives you the total charge. So you can write it also as integration of del rho by del t, because charge can change with respect to the position and time both. So we have to take the partial derivative, because it may be a function of x, y and z terms. So this is your, and it's integration over volume, so you must write 3 integrals. So this is I calculated in 2 ways. Now we can equate these 2 terms. So J dA equals integration del rho upon del T dV. Now current is passing through a cross section in a conductor, so we are taking a closed path to calculate the total current, so it must be a closed integral. So now you can apply the Gauss divergence theorem to convert this dA into volume integral. So we will write it as the volume integral of del dot J dot dA, dV. Now this dA term must go off and it must convert into dV. So this is your dV term and it's equal to, now there is a problem with sign. You know that in any situation, if charge is going out from a system, then it is causing the generation of current. So the amount of charge must decrease if the current is increasing. So there must be a negative sign with this, or you can simply write this as with a negative term here. So there is a minus term. Not in all situations it's minus dq by dt, but if charge is coming out, then there is a current, so that must be with a negative sign. So this is equal to minus del rho over del T times dV. So integrated over dV. So now if you compare these two equations, then you will get that del dot J equals minus del rho over del T. We will use this term here, but before that, just for your information, this del dot J, if this del rho upon del T term is taken in the left hand side, so del rho upon del T, then it gives you 0. This is known as continuity equation. It's same like when you study fluid mechanics, you study A1 V1 equals A2 V2, the continuity equation of fluid mechanics. In a similar manner, this is the continuity equation of electrodynamics. So we would rather have used, if you know this already, then you can directly write the value of del dot J from this continuity equation, although we have already derived this, but you can write it directly. So from this step we are getting that del dot del cross B equals mu naught times del dot J is equal to minus del rho upon del T. So this is what we are getting. Now we will write this rho term in terms of electric field. So how we can write this? You know that from the first equation we have E dot del dot E is equal to rho upon epsilon naught from the first equation of electromagnetism. So just write this rho term here. So you have to write it like this: mu naught times minus del over del T and this term rho will now be replaced by, here rho will be equal to epsilon naught times del dot E. So simply write this. So epsilon naught del dot E here. So we have written this. Now now we will have to write it as mu naught epsilon naught and this del term, we will swap these two differentials. So take this minus term out and write it as a swap of the differentials. So del dot del E by del T. So this is what you are getting. So now we will write these two terms together. So you see that this term is not actually equal to 0 because the electric field can change with respect to time, and so the divergence of curl which we expect to be 0, but this is not coming out to be 0. This del dot J term is not 0. This is equal to minus del rho by del T. So what we can do here, that if we instead of writing here mu naught J, if you write the combined term, then we will get 0. So what we expected, that this term, the divergence of the curl should be 0, but when the divergence taken on the right hand side, this term is actually this minus del rho upon del T, and this is what written here, and finally this was not going to be equal to 0, but this must be 0. So there is some missing term which we are not facing till now. So in one of the situation of capacitor, it was found that that is the case. We are not able to find why or how the current flows without any actual conduction between the plates. In case of capacitor, here is current and here is current, but there is no current. So without any current, this is basically an open circuit. How the charge can pass through it? So he thought that this is the missing term which is arising in case of capacitor. We will see this, but just we have to do complete the mathematical things first. So instead of writing this Ampere circuital law in this form, del cross B equals mu naught J, we must write it like this. This is not completely true, but it must be written like this: mu naught into J plus some term. There is something missing term here. So, and if this missing term, if we put this total thing here, then it will be 0. So that term is you calculated that this. So this was the formula which we used, and this is the term which we have calculated here. Now, so we have this del dot J term equal to minus del rho upon del T. So, and this del rho upon del t comes out to be this term, and we have written it as this term. So we will write it as del dot epsilon naught del E by del T. So this is what we have calculated. Now we will take the, and there is a minus sign here. So now we will take all these terms in the left hand side, and then you will get that del dot this j term plus this epsilon naught del E by del T equals 0. So now you see that that Ampere circuital law said that del cross B is equal to mu naught J, and if we take the divergence, then this term must be equal to 0. So this term must be 0, but you see that the divergence of this term is not 0. This is coming out to be this. So if we want a 0 in both sides, then instead of writing this term J, you have to replace this J by this complete term. So this is the missing term in the Ampere circuital law. So now the new law can be written as del cross B equals mu naught times this J term which was already there. Now this mu naught times J, and its divergence was not 0, but the divergence of this whole term was 0. So we have to add this term mu naught del E over del T. So this is the new law, modified Ampere's law, and it is called Ampere's Maxwell's law. Ampere's Maxwell law. To understand this new modified law, you have to imagine a physical situation of a capacitor. So I have already told that in case of a capacitor, there is a transfer of current charges, and in this wire, section of wire, you have current, and here you also have current, but in between them, between the plate, the circuit is opened. Then how the charges are flowing here? So how we can explain? And better, the main problem was not the flow of charges. It can be convinced in another manner like this. If you have a capacitor and you have connected it to a battery, then instead of charges flowing in between the plates, you can say that electrons are there and they are present on both the plates, and some of the electrons move from here to the positive plate. So loss of electrons create positive charge, and some of the electrons goes from the negative plate electrode of the battery to here. So some people used to explain this, and there is an electric field between the plates. So it was not the flow of charges which was the problem. The problem was with the calculation of magnetic field. So if you calculate the magnetic field at a point just above the or anywhere on this plate, you can calculate it anywhere, it will give you the same result. So if we want to calculate the magnetic field, suppose for at this point, then just before this point you have a current, but just after this point you have no current in this region. So we can calculate in a limiting situation where before that point and after that point. So in that case, if you calculate just before where the plate ends, you will find that you can easily calculate from Ampere circuital law, the old Ampere circuital law, that is integration of B dot dl gives you mu naught times I. So I am writing it in integral form because it will be appropriate here. So you can consider a loop. The plates are circular, these are circular plates, and you are finding the current, magnetic field here. So you can imagine a loop here, okay, and at this point the field is, I am drawing a bigger diagram. So you have a plate here and there is another plate here, and you are finding the magnetic field at this point. So magnetic field around a wire is like a loop. Suppose this is the current, so you calculate it by right hand rule. Just hold the wire and the thumb should be directed in the direction of current. Thumb should be in the direction of current. Then how the fingers of right hand curl gives you the direction of magnetic field. So at this point, when you draw the magnetic field at this point, the magnetic field points here, at this point magnetic field points here, at this point magnetic field will be here inside the plane of the paper of this board, and it is coming towards me and it is going away from me. So but the magnitude of the magnetic field will be constant if you are not changing the radius or this distance. So B must be outside of the integral, and integration this dl length, this is the length dl length. So if you calculate this, you will get 2 pi d, where d is the distance from the center. So it's equal to mu naught times I. So in this way you calculate B equals mu naught I upon 2 pi d. But what if you calculate the magnetic field just after it, okay, or anywhere inside this capacitor? Then you do not expect any magnetic field at any point inside or here, because there is no current flowing inside this capacitor, because there is no wire, connecting wire. So the magnetic field must be 0. But when you do it experimentally, you find that the same magnetic field, if you are at the same distance from this axis, then the magnetic field here and every point on this line must be same. So how this is possible? If there is no current inside this capacitor, then how it can generate a magnetic field here or here? So this it was already coming in the experiments, so we have to explain it theoretically. So what must be, Maxwell thought that there must be something there is that is generating the magnetic field, and he thought that there must be the change in electric field which is causing the generation of magnetic field. So if we just calculate the electric flux here, then what we get? So electric flux is given by E dot A. We are taking the area to be constant because area of the loop which you are taking is not changing, it is fixed. So the electric flux is given by E dot A. So now if the current is changing it was noticed that if when the current changes here, then there is change in magnetic field, and there is also change in magnetic field here. So let's find the derivative of this electric flux. So if you calculate the derivative of this electric flux d phi e upon dt, you will get d by dt of this E dot A term. But there is no need to take A because A is constant, so just take it outside. So this is d phi E by dt. Now this E can be written as for this capacitor as the electric field inside the capacitor is sigma upon epsilon naught. The electric fields of these two electrodes are sigma upon 2 epsilon naught, which add up to give you sigma upon epsilon naught. So we can put this term inside and you will get 1 upon epsilon naught times d sigma over dt times A, because E and A are parallel to each other. Here electric field is also here and the area vector is also perpendicular. So E vector and A vector being parallel here in our case, so cos 0 will give you 1. So these vector signs I have omitted. So this is the rate of change of electric flux. So now this d sigma upon dt, what is this? Now if we multiply sigma is the charge density, and if we multiply sigma with area, you get charge. So this is 1 upon epsilon naught times dq upon dt. This sigma is dq upon dA, and when this charge distribution is constant, then in that case sigma equals q upon A. So we have a constant charge density because charge is equally spread throughout the area of the plate. So sigma is constant everywhere in the area of the plate, so it is directly q upon A. So you can write sigma into A as q, so it becomes dq upon dt, and now it becomes dq by dt is equal to the current. So we have I upon epsilon naught equals d phi E by dt. So although there is no charge there, flow of charge there, but the charge density at the ends are changing, electric fields are changing, and this gives you some kind of current. It's not a current, but it gives you some kind of current. The effect of current, that is the production of magnetic field is there. So that current is referred as displacement current, and the current flowing in this wire is called conduction current. So this ID displacement current becomes epsilon naught times d phi E upon dt. So you have the now you can write the modified Ampere's law. So that will be, so initially we have the Ampere's law as B dot dl, the line integral of magnetic field was equal to mu naught times the I term. Now this I is for the wire, the current flowing in the wire, so we will call it conduction current, IC. Now as you know that at this point there was no current, and the changing electric fields produces the effects of magnetic field. So you can say that changing electric field is a kind of magnetic field. So we will write that current as ID, which is displacement current, and that ID we have already calculated. So it becomes mu naught times I plus IC was your I plus mu naught times epsilon naught d phi E upon dt. So now this is the Maxwell's law in a primitive form, Ampere-Maxwell law, and this is the way in which it's the differential, it's the integral form of Ampere-Maxwell law, and this is the differential form. So our next aim will be to convert this equation to this. So let's do this.